Welcome to this college algebra video on the topic of solving linear word problems. This is a follow-up to the video on solving linear equations. So if you would like, I would recommend going back and watching that video first, and then coming back and watching this video specifically about word problems. So the very first thing that I want to talk about here is how to start a word problem. Really what we're talking about here is mathematical modeling. We're trying to model the situation that's described to us using some kind of mathematical equation. And a lot of times students get stuck because they just don't know where to start. So I'm going to tell you that most linear word problems that you'll run into, not all, but a whole lot fall into one of two kind of categories. And once you understand these two categories, and can then start filling in the details, linear word problems, or any kind of word problems for that matter, are going to get a lot easier to you. So the two main formats that you're going to see in most linear word problems is this. One of them is of the format blank plus blank equals total. So two things combining to become a total. Sometimes it could be three things adding up to a total. Sometimes it's subtracting to get a total, but blank plus blank equals a total. We've got something we start with, something else, and we've got a result. So look for that type of a format. A second typical format for linear word problems is blank equal to blank. So when you're going to use this one is if you see a situation that is described in two different ways. Look for one description of the situation using quantities and another description of the situation, maybe just using numbers or possibly using numbers and variables. If you have two descriptions describing the same situation, we're going to set that up as blank is equal to blank. So throughout this section, watch for these two patterns, and I think you'll see them come up over and over again in a lot of different situations. So of course the details of how you fill in these blanks is going to really determine whether you can move forward with that problem or not. So here's the first example. Scooby runs from a ghost at 9 feet per second. Shaggy starts running 2 seconds later in the opposite direction at 5 feet per second. Of course, Shaggy has to spin his feet around in a circle for a little while before he can actually take off. So it's the way it works in cartoons. 2 seconds after Scooby runs, Shaggy runs. In how many seconds will they be 102 feet apart? So as I look at this problem, I see that overall I have a total distance for these two of 102 feet. 102 feet apart is made up of the distance that Scooby runs and the distance that Shaggy runs. So I'm going to set this up with the pattern blank plus blank equals total. If we can start with a pattern, then we go to the details of filling in each blank. And a lot of times it's easier to fill in smaller details than to just come up with an equation just from whole cloth. So we're going to try to fill in the first blank with the distance that Scooby runs. Well, we're going to need to remember a key fact here, that distance is equal to rate times time. Remember that relationship, rate times time. We're going to see it a few more times in the future. Distance is rate times time. So up in the problem, it tells us that Scooby's rate is 9 feet per second. I'm just going to call the time that he runs t. That's sort of what we're looking for here. How many seconds will they have to run before they're 102 feet apart? The next blank is for Shaggy. Shaggy starts running 2 seconds later. His speed, or his rate, is 5 feet per second. So I'm going to have the rate of 5 times an amount of time, but of course Shaggy had a delay. He doesn't get to run for as long as Scooby. His running time is 2 seconds less than Scooby. So when I multiply his rate times time, the time is represented as t minus 2. So the first blank is Scooby, second blank is Shaggy. Together, their distances all add up to 102. Well, now we've got a linear equation to solve. So we temporarily forget that this has anything to do with any kind of word problem. It's just an equation to solve. Let's follow the steps in solving an equation. I'll simplify this left side. So distribute 5 times t and 5 times -2. Next, simplify a little bit more. I could collect some like terms here. 9t and 5t can add up to 14t. 14t minus 10 equals 102. I've done all the simplifying I can. It's time to start undoing things to try to get at that t. I'm going to undo subtraction first, so I'll add 10 to both sides. We get 14t equals 112. If I divide by 14, 112 divided by 14 gives me 8 seconds. So 8 seconds after Scooby started running, when they saw that ghost, 8 seconds later, they are 102 feet apart. All right, here's a second example. Scrooge McDuck invested $4,900, part at 5% interest and the rest at 8% interest. I guess Huey, Louie, and Dewey were trying to influence him on how he should invest his money, and they couldn't agree. There's 2 different accounts that they want to invest this money into. So he's going to split up that $4,900. We don't know how much is going to go in each. He didn't say he was going to do it evenly, but all we know is that at the end of the year, he got interest of $336. So we're going to set up another skeleton of the problem. I sort of call these a skeleton if I don't fill in any blanks, and then I start putting the meat on the bones. But the skeleton is the same kind of pattern that we saw in the last problem. Blank plus blank equals a total. This time our total is the $336 of interest. All right, well, just like last time we had rate times time equals distance. This time we're going to look at another pretty common relationship. For simple interest, rate times dollars is equal to simple interest. So not a rate times a time, but rate times dollars this time. The rate for one of the investments is 5%. I'm going to call that as the decimal 0.05 times an amount of money X. I don't know how much money he's putting into that account, but it's some of that $4,900. For the next blank, I'm going to go with the interest rate of 8%, written as a decimal, 0.08. But how much money is left to put into that account? We start with 49. We've already used X. What is left is 4,900 minus X. And if you check, all this added together, X plus 4,900 minus X, totals up to 4,900, all the money that Scrooge McDuck started with. Well, here I've got a linear equation. I'm going to start solving this linear equation, do the same kind of steps I did before, simplify the left side, and then I'll start trying to get X by itself. 0.08 times 4,900 is actually equal to 392. And don't forget to multiply 0.08 times this negative X. Let's collect some like terms here. Altogether, I'm going to have negative 0.03x plus 392 equals 396. I've simplified as much as I can. Let's start solving for x. Let's subtract 392 from both sides. I now have negative 0.03x equals negative 56. Got a calculator. It's not too difficult to divide both sides by negative 0.03. Negative divided by negative gives me positive, and 56 divided by 0.03 is about 1,866.67. So what that tells me now is the amount of money that Scrooge McDuck put into one of the accounts. Remember, X was in the blank with the 5% interest. So this amount of money goes with the 5% interest. And we still need to finish answering the question because it asked how much was invested in each account. The other account had 8% interest. The amount of money was 4,900 minus whatever money was put into the first account. So 4,900 minus 1,866.67 leaves a total of $3,033.33. And that's the amount of money put into the 8% account. Now, a lot of students are uncomfortable working with these decimals, so let me show you a slightly different way to solve this problem. And this goes back to one of the lessons I talked about on solving linear equations. A common thing that we do with linear equations is that we can multiply all the terms by 10 or 100 or 1,000 to be able to clear decimals. In this case, each of these decimals was a 2-digit decimal, so I multiplied every term times 100. I got 5x, and I got 8 times 4,900, and I got 8 times negative x. When you do this technique, don't forget the other side of the equation must also be multiplied times 100, 33,600. So if I've cleared all the decimals, some people are just a little more comfortable working with whole numbers than with decimals. The rest of the process for solving is almost the same. Combine your like terms. This is a negative 3x over here. When I subtract 39,200, I've got negative 3x equal negative 5,600. Divide both sides by negative 3, and we come up with the same answers as before. We don't come up with 100 times the number of dollars or anything. The solution to the equation stays the same, no matter if we use this trick of clearing decimals or not. So we wind up with the same amount in the 5% and the same amount in the 8%. Before we start the next example, I've got a little question for you to consider here. I want you to read this screen, see if you can answer those questions relating to each of these people here. I'll let you pause the video, and then in just a second, I will go over the answers with you. All right, if you've had time to try this yourself, let's start with Joe the plumber here. Joe, I talked to him and asked him, hey, how long is it going to take you to replace the pipes and faucets and everything in my shower and tub? And Joe tells me it'll take him 7 hours to do the whole thing. So how much of the job can he do in 1 hour? Hopefully, if you answered 1/7, you're correct. He can do 1/7 of the job in 1 hour. He can do 2/7 of the job in 2 hours. He can do 5/7 of the job in 5 hours, and he can do T/7 of the job in T hours. Of course, if he works for all 7 hours, that's 7/7, and he's done 1 complete job. So I go and ask Sally the plumber the same question. She says, hey, I can do that whole job for you in 6 hours. So the same questions for her. How much of the job can she do in 1 hour? She can do 1/6 of the job. In 2 hours, 2/6 of the job. And in 5 hours, 5/6 of the job. In T hours, Sally can do T/6 of the job. Now, I ran into this alien the other day. His name was Zork, and he said that he could do the job in N hours. Well, he didn't actually say N hours. He gave me some kind of incomprehensible unit of time that they use on his planet. I couldn't tell what he meant. So I just said, well, it's N hours, and I'm going to try to answer those same questions because I couldn't quite get exactly a number of hours, but it's some number, some amount of time here. But could I answer the same questions for Zork? Let's try it. The first answer, 1/n. In 1 hour, he can do 1/n of the job. In 2 hours, he can do 2/n of the job. So whether that n was 10 hours or 5 hours or 16 hours or 1 hour, this is how I'd find the amount of time or amount of work he can do in 1 hour and 2 hours. 5 hours, he can do 5/n amount of the job, that fraction of the job. And in T hours, we're following the same pattern we did for those other questions, Zork can do T/n of the job. Now, if you split this up, really what this breaks down to is 1/n times T. And what this is, it's a rate of work times a time. Again, we see rate times time, just like we saw with the distance was rate times time. This time we're going to talk about work being rate times time. So let's bring this all back to a linear word problem. So the word problem that we're interested in is this one. How long would it take Sally and Joe, both plumbers, to finish the shower tub job working together? Now, one of them can do it in 6 hours. One of them can do it in 7 hours. Add those together, you get 13. Wait a minute, that doesn't make any sense. If they work together, it should be less time than working apart. So sounds like we need to solve this with an equation. Once again, the pattern of this equation is going to be blank plus blank equals total. This time, the total amount that we want to get done is one job, and this is typical of these work problems. We're going to add up the work done by one person or a machine, and we'll add up the work done by another person or machine, and in total, we want to get one complete job finished. Now let's fill in the details of what we're adding here. Now, just like in the problem we just looked at, we're going to be finding the work done by multiplying a work rate times a time. So that's how we're going to fill in those blanks. Our work rate is going to be 1 over the number of hours that it takes the person to do the job, and then the time is going to be T. So I'm going to start with Sally, who can do the job at a work rate of 1 over 6 times T. Then I'm going to take Joe. He can work at a rate of 1 over 7 times T. So remember, she gets T over 6 of the job done in T hours. He gets T over 7 of the job done in T hours. Now let's solve this linear equation. Well, a linear equation that has fractions, our strategy for that is to multiply by the lowest common denominator. 6 and 7 both go into 42, so I'm going to multiply all the terms in this equation times 42. The resulting equation should not have any fractions anymore. And in fact, it doesn't. It equals 7t plus 6t equal to 42. Add up 6 and 7t and you'll get 13t equals 42. So the time required is 42 over 13. Now in terms of hours, that is 3.23 hours, or if we want to turn that into hours and minutes, take the decimal part of this to 0.23 and multiply times 60. And we'll see that it's 3 hours and 13.8 minutes. Our next example is a typical problem that's found in a lot of algebra textbooks. These are called consecutive integer problems. Starts out, find 3 consecutive even integers such that if the largest integer is subtracted from 4 times the smallest, the result is 6 more than twice the middle integer. Wow, that sounds a bit complicated, but I think I can write sort of a skeleton of the problem. It says one thing is subtracted from something else and the result is something. So I'm just going to put in a basic 3 blanks here. So that I can subtract something from something else and get a result. Now it comes to the time of filling in the details of these blanks. Now, just so that we can get a handle on this problem and get a start, I'm going to write what is sort of a half literal and half algebraic equation. I've got those operations in here. I'm just going to fill in with a little bit of the wording that was used up in the paragraph. It says something is subtracted. Well, the largest integers. I'm going to put biggest in that blank. So that's what's subtracted from 4 times the smallest. So here I'm just writing 4 times the smallest. The result is supposed to be 6 more than twice the middle. So 6 plus 2 times the middle. Now we're going to try to fill in the details of what the smallest, biggest, and middle integers look like. I'm going to call the smallest integer n. And as we try to list some more integers, we always follow a certain pattern here. With consecutive even integers, the next integer is going to be 2 away from the smallest. So n plus 2. The next integer is going to be 2 more than that. So n plus 4. These are the smallest, middle, and biggest integers represented algebraically. We'll talk a little bit more about how to represent integers in just a second. So using these 3 representations, n and n plus 2 and n plus 4, I can rewrite this equation now as 4 times n minus n plus 4, that's the biggest of these 3, equals 6 plus 2 times the middle, which is n plus 2. So I'm going from a paragraph to a sort of quasi-algebra, a little bit of English, to a completely algebraic equation. It's one of the strategies that you can use as you solve word problems. Now, we need to simplify both sides and see about solving this equation. The left side, 4n minus n minus 4, can simplify to 3n minus 4. The right side, 6 plus 2n plus 4, can simplify to 2n plus 10. I'll subtract 2n from both sides to get all the n's on one side, and I will add 4 to both sides to get all the numbers on one side. And the solution of that equation is n equals 14. Now, of course, that is not the answer to the question. The question said find 3 consecutive even integers. One of those integers is 14. Now, that's the smallest. If I look back up here and identify n was the smallest of my integers. The middle is 2 more than that, which should be 16. And the biggest is 2 more than that, which should be 18. So we've got n plus 2, and n plus 4 being 14, 16, and 18. Just want to make a quick note here about listing consecutive integers. Consecutive integers themselves, if we don't worry about even or odd, consecutive integers can be listed as n plus 1, n plus 2, n plus 3. Because if I start with an integer and add 1, 2, and 3, I'm getting the next few integers down the line. Consecutive evens, as we just said, look like n plus 2, n plus 4, and so on. What's unusual is that consecutive odds also look the same. n plus 2, n plus 4. And that's because consecutive odd numbers are 2 away from each other as well. If I want to go from 5 to 7, I go 2. If I want to go from 5 to 9, another odd number, I add 4. So I add 2 or 4 or 6 to get from one odd number to another. It seems like it would be plus 1, plus 3, or something like that for odds, but no, it looks exactly the same as for consecutive even integers. My next example is going to be an example of the other type of pattern that I talked about for linear equations. The blank is equal to blank. It says Gary bought an MP3 player at 20% discount sale for $52. What was the original price of the MP3 player? So remember, for blank equals blank, we're sort of looking for 2 descriptions of the same thing. So in words, what I'm kind of filling into these blanks is the following. What he paid is equal to what he paid. So can't deny the truth of that. That certainly is a true statement. What he paid is equal to what he paid. But we're going to describe what he paid in 2 different ways. On the left side, I'm going to describe this discount. On the right side, I'm just going to describe it as $52. So at a 20% discount from the original price means that the amount he actually paid was 80% of the original price. So on this side, I put 0.8 times P, that represents the original price. On the other side of the equation, I've got 52, because that's another description for what he paid. This is a very simple equation to solve. Just divide both sides by 0.8, and we get original price of $65. For our last example, we're going to see an equation that could be set up in either way. One description might be the blank plus blank equals total, or the other is just blank equal to blank. So I'll show you both ways to set this up. So first of all, our total amount is $97.50. That's the amount Carla sold her bike for. It says the selling price represented a 30% profit for her based on what she originally paid for the bike. So bear in mind, this 30% is not 30% of the price that she sold it for. It's 30% of what the bike originally cost. So in one of these blanks, I'm going to put her original cost for the bike, because she certainly wants to get at least that much back for the bike, but she also wants to make profit. So the added part is the profit that she makes. This is going to be 30% of the original cost, or 0.3 times C. If we wanted to combine these things, we could say that her selling price is 130% of her original cost. So in this blank, I could put 1.3 times C. That would be 130% of the original cost. Of course, if we start with this and immediately simplify, we'll go straight to 1.3 C equals 97.5. So really, whichever approach you take, you're going to wind up with the same answer. When we divide by 1.3 on both sides, we'll find that the original cost was $75. So thank you for watching this college algebra video. Hopefully this will help you in setting up some word problems, whatever types that you have to solve.